So, hello everyone. Let's now start our perhaps the last class of this course, APL 104. And we take off, we were discussing the examples of instability in the last class. So, we'll discuss a couple of other examples before we take one of them to detail. So another instance of buckling, as it says, the author says in your textbook, another instance of buckling of a thin-walled cylinder was mentioned in section 6.6. Okay, so let's see, did we do that section 6.6? Yes, so we had done this torsion of elastic hollow circular shafts in which we created this shaft by removing material from it. Okay, and then we had made certain comparisons about the maximum shear stresses. So a similar thing is what we are seeing over here, that we have when such a cylinder, it's a hollow cylinder, is subjected to torsion, it will remain cylindrical. Okay, and deformation will be of the type which we have considered in chapter 6 if the applied twisting moment is small. That's the important part. When the twisting moment surpasses a certain critical value, so when mt surpasses this mt critical, at that case the symmetrical deformation becomes unstable. So the deformation, the configuration at that point is unstable, and a small disturbance will cause the walls to buckle into wavy shapes. So this is what happens, buckle into wavy shapes, where the crests of the waves lie along helices which are 45-degree with the axis of the cylinder. So this is, this is, as you can, this is not a planar movement. Okay, so it is lying like a helix from this axis, and this is something which you can again easily observe if you see a cylindrical, like the straw for example. Okay, the straw through which maybe we drink juices and cold drinks, you can apply you can see, observe this sort of a deformation, this type of a buckling. So we have earlier seen the buckling in this axial loading, and this is the buckling and tension. Okay, now it was noted in 7.6 that if the compression flange or the web of an I-beam is made too thin, there is a strong likelihood. Remember, we had done this discussion. Actually, we left it out for you to read it at a later time. So this is that time. So it was noted in section 7.6 that if the compression flange or the web of an I-beam, this is the web, is made too thin, there is a strong likelihood that there will be a local buckling when a bending load is placed on the beam. So if you have a bending load, and if this section, the web is too thin, then there is a buckling which may happen. A similar type of buckling can sometimes be observed by passengers sitting over the wing of an airplane when the air is rough. During momentarily peak loads, the top surface of the wing will distort into a rippled shape as the thin skin buckles locally under compression. So see if you can find something about this over the internet. Okay, buckling in the airplane wing, and see if you can find a picture of a video which you can perhaps see, and then you must apply the concepts of fluid mechanics and see how the loading must happen over there. So there is a part above and below the wing, so you should be able to see how that works out. Okay, so this is something which we had left in section 7.6, and if you are not sure, please go back to section 7.6, see this paragraph, and then come back to this place. Okay, so in figure 9.9, The flexible shaft is being twisted by equal and opposite moments directed along the line AB. So, okay, if the twisting moment is small, the axis of the shaft remains collinear with AB and the shaft is twisted uniformly. When the T becomes larger than a critical value, the straight configuration becomes unstable, and then you have this sort of a spiral behavior which we have seen. Okay. So that is one example, and I think we have earlier discussed it again in the wavy shape. So both of them you can have a look. Okay, so both of them should be okay. Okay, now a somewhat different sort of instability is shown in figure 9.10. So what you have over here is a shallow curved member. So this is the shallow curved member. It is subjected to a load which tends to straighten out the member. Okay, this is a load, and if you look at it, it tends to straighten this out. If you have small values of P, only small deflections result, and those are shown by the dashed lines over here. Okay, but at a critical value of P, the member suddenly snaps through to the position of opposite curvature like this. Okay, if P is greater than P critical, then there is a chance that any small disturbance beyond will help you get like this. Now in many cases, I mean, though even though it is a so-called instability, this behavior, in many cases it is actually desired, like the electric switches. If you are ever get a chance to look at how an electric switch looks like, they have a small plate like this, and then you apply a load and it comes to the other side. So then there is a switching on and off mechanism. So please see how electric switch works. You should be able to see this, and perhaps you will see that an instability like this is actually desirable in certain cases. Okay, so that's where we were with the examples, and let's see how the instability of a flexible column can be studied. So out of all the examples which we have just described, we shall investigate only one in full detail. This one. This is something which we'll see in full detail right now. Okay. The buckling of a column which is built in at its base. Our reasoning and general approach can be extended to many other cases, but the mathematical complications increases rapidly when we consider systems with more complex geometry. So before considering the stability problem, we first derive the equations governing the bending of beam subjected to longitudinal as well as transverse load. Okay, so in this figure 9.11, if you see, we show a portion of a beam like this. So it has a longitudinal force P and the shear force V. Okay, and it is being so we also have this Q of x, which is the force intensity. Now if this particular element has to be in equilibrium, the first thing is the force equilibrium. So if the length of this is delta x, okay, so and there will be a change in shear stress, there will be a change in bending moment. So this is not d, it's a delta mb. So you can make this correction in the textbook. Okay, so it is v and mb over here, v plus delta v and mb plus delta mb on the other side. Okay, fine. So for the force balance to work on this element, small element of the beam, we have v plus delta v minus v plus q into delta x is equal to 0. Similarly, we will have an mb plus delta mb minus mb plus v into delta x by 2. we are taking about the center plus v plus delta v into delta x by 2 plus p delta v equal to 0. Okay, so this is the center, and of course this p will not have a this moment of a force will not exist because it passes through the point, but this particular p will. So that's p delta v, and this delta v is the small displacement. So this v, I'm sorry, this v was actually the deflection. Okay, so small v is the deflection, big V is the shear force. So this is the small v over here. Okay, so this point which you see, so let me zoom this out. This point which is pointed out over here, this is actually this point, and delta v is slightly above this. Okay, fine. So this is done, and then you want to use the limiting cases where delta x tends to 0, and then you will be able to convert it to dv by dx plus q is equal to 0 and dmb by dx plus v plus p dv by dx equal to 0. Okay, so you will also ignore some of the terms which are small, like for example delta v into delta x is made up of two very small terms, so they'll be 0. The product of that will be 0. Okay, so that's the higher infinitesimal of higher order. That is what we mean by discarding the infinitesimal of higher order. So two higher order terms like cubic or squared of smaller terms, infinitely small terms, will be ignored. Now these should be compared with 3.11 and 3.12, which are the corresponding equilibrium equations when p is equal to 0. So please check. So this is 9.4. Please check 3.11 and 3.12, which we had done this for a case where p was equal to 0. So let's see what that equation looks like. Yes, so that looks like dv by dx plus q equal to 0, and then dmb by dx plus v is equal to 0. Okay, and note that the deformation of the beam enters into the moment equilibrium equation of 9.4 by way of the slope dv by dx. Okay, so this is how the deflection enters, deformation of the beam enters this equation through this term dv by dx. We still assume that the bending moment is responsible for the deformation of the beam, that is, we neglect the effect of shear on the deformation. According to 8.4, which we had derived in the earlier section, you had EI d2v by dx square equal to mb. Okay, and EI is the bending stiffness or the flexural rigidity of the beam. Now you want to eliminate mb, so what you do is you please put this mb into this equation, and then you will arrive at this equation, which is 9.6. So you would have a d2 by dx square mb EI d2v by dx. Okay, so that's what you would be getting. You want to put this into this 9.4, okay, mb over here, and you will be first getting it in this term, and then you also have 9.5. Where did it go? This is 9.5. So between 9.5 and 9.4 you can eliminate mb. So the idea is you just put mb over here, okay, and you should be ending up with this equation. Okay, because V also comes up over here, so that also you will have to take care. So there's a two-time differentiation. Once you will put MB over here, and then V also has to be differentiated for this. So you'll be finally getting this equation. So this is valid obviously for small deflections of the beam which are subjected to transverse load Q of X per unit length and an axial compressive uh, force which is P of X. We now return to the elastic stability problem. So this was all elasticity, okay, equilibrium situation. Why equilibrium? Because I mean we had this, right? This had come because the forces and moments in this element were in equilibrium. So that's how we had written that. Okay, and so now shown here again. So we show the same figure which was there in 9.7. This was sort of vertical. We have now aligned it like this. So just so that it matches our convention and the terms which we have. So we have this P force applied like this. We take the beam to have a uniform bending stiffness EI. So EI is constant, and you assume that the buckling occurs in the plane of the sketch. So that is one other assumption. There is no out of plane buckling. If the beam should be accidentally displaced from a straight position, the force P produces a bending moment along the beam, which causes the beam to bend even further, while the elastic forces in the beam tend to restore the original position. Okay, so you know the two competing things now. What are the competing things? That P will try to unsettle, and then the elastic parts within, like the stresses and the forces within, okay, they would try to have a restoring effect. Just like in the earlier cases, the load P was giving a unsettling torque and the springs were giving the restoring torque. Okay, so we'll see how that compares over here. Now for small loads, the straight position is stable and the beam is subjected to uniform compression. Well, we know that. Okay, now let's see this one at a time. Okay, for large loads, the straight position is unstable and the beam buckles. The most important single result to be obtained is the value of the critical load, which marks the border between stability and instability. So we can get this result by arguing that when the critical load is acting, the restoring tendencies just balance the upsetting tendencies and the system is in a state of neutral equilibrium. Okay, so we want P to be such that it is at that border between restoring and upsetting tendencies. Okay, so we want that to be at this critical value. Now in figure 9.12, we assume that the critical load is acting. So now P is critical, and then it is holding the beam in equilibrium in a displaced position. So this is like the max it can go to hold it in equilibrium. Beyond this, it will not be able to hold it, and hence it will be unstable after this value. The magnitude of the critical load and shape of the bent beam are initially unknown. That's like with all the examples also we have discussed. So as of now it's unknown, but we will have to find it because we are doing a detailed analysis in this section. So we cannot just say that P has to be greater than some critical value. So we'll see that how we can do that. Okay. So for this we'll have to solve this the 9.6, and then we have to put the conditions at x equal to 0 and x equal to L. So let's see, at x equal to 0 the deflection is 0 and dv by dx is also equal to 0. At x equal to L what would be 0? Clearly V is not 0. Okay, but one thing is for sure, the shear force is 0, capital V is 0, and then the bending moment is also 0. These things are not 0 over here. So this is the again the deflection or the displacement. Deflection. Okay, and this is the shear force. So at the end, at x equal to L, you see that there is only an axial force. There is no shear force or bending moment. So these are the 4 conditions, and that is all you require, right? I mean, to find the 4, because this will throw up 4 unknowns, and you should have these 4 equations with you. Okay. So you can put all of it in, and then we can write this equation as EI, this 9.6 over here, as EI d4 V by dx plus okay, so this becomes this. Okay, obviously what we have assumed as is EI and P are constant. Okay, and there is no transverse load. So our problem is to find the equilibrium configuration V of x, small v of x, and the critical load P, which simultaneously satisfy this equation. Okay, because at the critical position you are still in equilibrium, and that is what we have done over here. Okay, at equilibrium position you are still in equilibrium. That is what we want to sort of exploit. Yes, beyond that we won't be. And then there are these boundary conditions which we have just noted. So we want to find a V and P which satisfy this, but P is the critical load and V is the deflection, okay, or the so-called equilibrium. So the deflection will be called as equilibrium configuration V of x. Okay, so that's done. So it is interesting to note that Vx equal to 0 satisfies these for any value of P. Okay, you can look at this equation and you will notice that Vx equal to 0 will be satisfying the equation for any P. Okay, this means simply that the straight position of the column is always a possible equilibrium solution. Okay, we knew this physically, but this is just to like say this, that this position is always in equilibrium. It's always an equilibrium configuration. Okay, this is like in mathematics you say something called a trivial solution, so it's more like this. It's something which is trivially known. You don't have to work really hard for it. As far as the buckling position, buckling problem goes, this must be considered a trivial solution. We are seeking the non-straight. What we are looking for is another neutral equilibrium condition, which is at the border between upsetting and restoring situation, or this in between stable and unstable equilibrium, the so-called non. So we are looking for a curved configuration like this, which is at this critical junction between stable and unstable. That is what we want to do. Okay, now we want, so you may have learned by this time how to be able to solve differential equations, because that will come in handy right now. So for this equation, the most general solution, meaning v of x, it will have four independent constants of integration, and for certain equations including this one, there exist routine methods for obtaining general solutions. Okay, so you should first of example know how to solve this analytically. If you do not know how to solve a differential equation of this form, you have to go and check your mathematics courses which you have done, verify that you know the method, and then come back to it, then solve it. That's the most important part. You should be able to solve it to get an answer which looks like this. See, I wouldn't have asked you to do this if it was a differential equation which was so-called outside your syllabus or something which you had not learned before. Okay, so by this stage among your mathematics courses, you should have learned how to solve this equation, and then this is the answer which you would get. Okay, these are the four constants, and then you would be able to substitute the boundary conditions, okay, which you have seen over here. 9.7 is the boundary condition. Where did it go? Over here. This is the boundary condition 9.7. So there are four of them, 1 2 3 4. Okay, 3 4. So that you will have to put, and you will find the value of c1 c2 c3 c4, and once you substitute all of this back, you should be able to find those. I mean, you have to substitute them first. So this again, I mean, what you have to do is this: you have a linear equation and it will be equal to 0 or something else. So you will get a system of linear equations, 4 into 4. So you can solve it using the Gauss elimination method or any other method which you seem are okay. Okay, and either way you should be able to solve it. So if you are not sure how to solve it, you can read your textbook, or you can go back to your maths where you studied linear algebra. One of the reasons I am telling you to go back to your maths course and see the method is that you may not actually encounter a differential equation which is exactly like this. And at that point, you cannot say that this was not there in the book or this was not covered in the book. Because you may get a differential equation which is of a slightly different form. You may get a 4x4 system of simultaneous equations when you put in the boundary conditions of a slightly different form. Hence, I am saying that you should actually learn the methods, and if it's not taught in the maths course, if it's not there in your maths textbook, then it is fine for you to say, well, I don't deserve to know this. Okay, and then it's something which is responsibility of me or any other instructor to tell you that. But because these things are definitely there in your earlier courses, please go back and check that. Okay, so you will eventually find that P is equal to pi square by 4 is the critical value, EI by L square, and then you will have a corresponding deflection as well. Okay, V as a function of X. So we have found the critical load and the shape. So this is the deflection or the equilibrium configuration, and which the beam bends into when balancing the critical load. Now we want to sort of take it a step further. So this is what it takes to find the critical load. Remember when we had said P critical in the earlier case about 2KL, it was easy there, but it took an effort like this to find what the critical load and the uh, configuration is at that point. Okay. Now note that in 9.15 the constant C1 has not been fixed. So what happened over here was this V of x was equal to C1 1 minus cos pi by 2 x by L. We didn't actually fix what C1, this constant, was, this particular thing. And the deflection is an equilibrium position for any arbitrary value of C as long as the deflection remains within the validity of small deflection theory. It can be shown that these are all neutral configuration positions, that is, the critical load will hold any of these deflections in equilibrium. For smaller values of P, the straight column is stable. Okay. If any accidental bending occurs, the restoring tendencies overcome the upsetting tendencies. For larger values of P, the straight position is no longer stable. Any small disturbance will result in buckling of the column. Okay. So that is one insight, that C is not fixed. What do you get? I mean, you get so-called this family of configurations. Okay. All of them will, so X is anyways there, but with C1 being arbitrary, you get all these family of terms. Okay. You can fix C1. Okay. I mean, if you get around, you can fix C1. That will also be one of the answers. But if you want to keep one constant, one of these constants as free using the method which the book has discussed, you get this family of uh, family of deflections, configurations, okay, which will still be acting at the critical value. Now, you have an additional insight. If there is an imperfections like this, okay, and remember we included the imperfection with the eccentricity, and this was not necessarily because P was not acting in the center, but due to any other error as well. Okay, so the column is slightly bent in it. So additional insights into the column buckling can be obtained by considering a case where there is a small imperfection in either the column or the loading. Example, the column is slightly bent in its unloaded state. So this is how the unloaded state looks like, and it is slightly bent, not exactly straight. Okay. As an illustration, we examine the case shown in figure 913a, where the compressive load P is applied with a small eccentricity epsilon. This is statically equivalent to a central force P, and a moment m naught is equal to P epsilon. So this thing is statically equivalent to force which is acting exactly at the center, and this moment m naught which is equal to P epsilon. Okay, so once this is done, and perhaps I think you should know why we are doing, I mean, we have done something similar before, and you may get a hint of why we have converted it to something like this. Because most of the solutions, say, of deflections of a beam are known for this situation where P is acting in the center and there's a moment acting like this, but they are not known for this sort of a situation. So to convert this into the deflections which you already know, like the delta table 8.1, if I remember correctly, okay, that is why we are trying to convert this into it, because this deflections due to this loading are not known as a standard. You can always derive it, but we want to convert it to something which we already know. Okay, so that's where this 9.13b is coming in. Now a graphical demonstration of the equivalence is displayed. So this part you have already seen before. It's the same thing in the very first chapter, I think, the friction in the pin joint, and then it was displaced by a certain value, and similar force equivalence is there, statically equivalent systems, again coming back as a legacy from your APL 100 in your last first year course. Okay, we shall now investigate the relations between the transverse deflection delta. This is the transverse deflection delta, and the compressive force P in the presence of bending moment m naught due to eccentricity epsilon. Okay, so you want to now study this delta with the relationship with P and the bending moment m naught due to eccentricity E. So eccentricity will now be contained in this term m naught. Okay, the governing equation is still 9.9. Okay, 9.9 is this one. This is still the governing equation, but there are minor changes. Except that at x equal to L now, what are the boundary conditions which have changed? Well, over here nothing has changed. V is equal to 0 and the curvature is 0. But at x equal to L, something has happened. At x equal to L, capital V is still equal to 0, but MV is equal to M naught now. Okay, which was 0 in the earlier case. So this is the only difference. And then you sort of repeat the same analysis and you should be able to find value of delta versus P. Okay, so you should have a relationship between delta and P, so that would be delta is equal to epsilon sec rho P by EI L minus 1. Okay, this is equivalent to your what, P versus X in this situation which we had seen in the last class. So you had a P and then it was displaced by X. So this is that graph. Okay, and P critical again is something which we have calculated before, and we had done that for, I think, x equal to 0. Okay, so P critical was pi square by 4 EI by L square, and this is known now. So this part is again stable and this part should be unstable. So the analysis is similar for this part. For small values of P, the transverse deflection is very nearly 0. For this example, delta is smaller than eccentricity for P smaller than 4 by 9 of P critical. Okay, so that is the first part. You don't see the graph, the behavior of the graph is different than it was in the last case. But one thing is definitely for sure, I mean the eccentricity delta is small. This delta would be small if P is very small, and that is obvious as well. As P approaches the critical load, the deflection delta becomes large. As you can see, as you keep on increasing, going up on P, the delta will also increase. And it can be shown that when P is greater than the critical load, the equilibrium positions represented by 9.18 are unstable. So this, as we had said, this was a borderline case between stable and unstable, and we derived it from the stable perspective. But you can also see it from an unstable perspective, that when P is actually slightly greater than the critical load, then this defines your unstable equilibrium configuration. Thus, a flexible column can be used as a reliable structural element only when the axial compressive force which it carries remains somewhat below the critical load. Okay, now the critical load of a column is quite sensitive to the nature of the supports at the ends of the column. So, I think we are discussing this over here. So we have taken a case in which P was coming down like this, okay, like this one. But if you had these roller supports which will force this movement to be only in the vertical direction, okay, and there are other cases which we discuss. So what the point is that the critical load, so P critical, is very sensitive to the nature of the supports at the ends of the column. In figure 9.15, a number of different methods of column support are shown, together with the critical loads which were obtained from analysis similar to one just given above. Okay, so we will have some problems related to this. Note that the critical load of a column which is clamped at both ends is 16 times larger compared to the case which is just discussed. So this is the case which people are referring to. This is clamped on both the ends. Okay, so it can only move in this form. Okay, in practical structures, the and this is how you are calculating the critical load. So you see, critical load was actually this pi square 4 by ei l square. So ei by l square is so called the property of a material. Okay, so that's why you are only considering this pi square by 4 for the critical value. And in this particular case, you are able to find out that this will be around 40, this will be around 2.4, and that's why they say 16.9. So most column supports provide more restraint than a hinged joint, but not as much restraint as a clamped joint. So somewhere in between is what you would have your P critical. This is the idealized case, no support at all, and this is like clamp joint, but in reality most of them are somewhere in between. So in many cases, a designer can use his or her judgment and experience to interpolate between tabulated results such as those given in figure 9.15. So okay, so you can have different cases and see how you are going to design your structure so that a P critical can be con. And why is P critical so important? As a designer, this is perhaps the only thing which you are able to control, because you will not be able to control, say, when a tremor is felt or a large wind passes through a building or a structure. Okay, a high speed wind. This is the only thing which you can control, and because anything beyond P is greater than P critical, anything which happens beyond this is not under your control. So best you can control this P critical, and that's why they devise these different settings towards the end. And perhaps in problem 9.8 and 9.9, which will be done as a tutorial, you will be able to figure this part out. Okay, so what to use in between. Okay, so this sort of winds up all the content of this course, and I hope you had a wonderful experience learning this course. I do understand the method of this course would have been different to you, but I also hope the difference would have been in a good way. In the